Okay, good afternoon, one and all. Today, I'm going to take one more class for completing this particular chapter. Under any circumstances, we shall complete the chapter number 3 today itself. And there is a one important problem. Just now, I have gone through the previous question papers of your seniors. A very, very important question. Repeatedly, you are asked to determine the Nyquist rate, and Nyquist frequency. Is a very, very easiest problem, and most of the times you are getting this problem for 7 marks, 7 to 10 marks. Okay, that is the easiness of the problems that we are going to solve in this particular chapter, right? So without wasting our time, let us continue the actual topics. uh, Let me share my screen here. First, let me share my screen here. Now, is it okay? Is my screen is visible to all of you? Is my screen is visible to all of you?
Yes, sir.
Okay, right. Now, see here. For your sake, I am zooming this document. Right. I think now it is visible to all of you, right? See, already we have seen three types of samplings are there. The first one is natural sampling or ideal sampling. So in that particular case, we have taken an ideal sampler. See, ideal sampler means we are going to consider an impulse train which is defined from minus infinity to plus infinity. The pulse duration is equal to 0 seconds. But in practice, you should not have a ideal sampler. So ideal sampler will produce ideal impulses defined from minus infinity to plus infinity. Already we have seen the generalized expression also. Okay, so after that, that ideal sampler has been replaced by a pulse sampling. So ideal sampler means we should not get the sample. Just wait a moment. I will draw it. I will draw it here. Now, now see here. So ideal means just you are having only a pulse. A pulse. You should not have any pulse duration. Duration means, now see here. So this is also impulse. This is also impulse with the pulse duration p. With the pulse duration p. Now this is denoted with the delta of t. Once if you make this p is equal to 0, then you will get this impulse signal. This is also delta of t. But whenever we are speaking or whenever we are talking about the practical situation, you may have this type of impulse signals, not this one. This is ideal case. This is completely ideal case. So whenever I am using ideal means no one is ideal here. Okay, so be practical. So this is a practical sampler. This is a practical sampler. So when we are dealing the sampling with the use of impulse train, which is like this, obviously that is an ideal sampler. Ideal sampler. Now this is pulse sampler. Pulse sampler. So the, you may have number of pulses which are defined from minus infinity to plus infinity. Only for your understanding, I have drawn only one pulse. One pulse, that too at time t is equal to 0. And you will have infinite number of pulses which are defined from minus infinity to plus infinity. Right? Some of your friends are waiting for me. Say I'm taking the full control over this session. You should not have any control for unmuting yourself, right? Okay. So this is ideal case, and this is a pulse sampling case. So pulses means you should have this type of pulses defined from minus infinity to plus infinity. This is what we have seen in the two sampling processes we have seen in the last level we have discussed in the last classes, right? Now today we are going to deal with the one more sampling process. So before going to that, first of all, I want to explain one important, very, very important point here. You just go through this. Pulse sampling, I think, right, it is the pulse sampling, right. Now, the very, very important, step, you just see the sampled output signal. Suppose this is the given signal x of t. Let us consider, this is our assumption. Let x of t be now this is the a sinusoidal shape, not sinusoidal, just it looks like a sinusoidal shape. So this is my assumption. I am considering this x of t is defined like this. Now this is multiplied by, if this is multiplied by, now see here, if this is multiplied by a series of pulses, just wait a moment, I shall use another color, right, pink. Okay, now see here, no, this is also not suitable color, just we shall use black, right. Now see it, observe the difference between the previous sampling and this sampling. In the previous case, you will have ideal samples. Ideal samples means you should not have any pulse duration. You should not have any pulse duration. But in this case, you will have certain pulse duration. We don't bother about the pulse duration, but we will definitely have that pulse durations, right? Now see it. Now see it. So this is the pulse train. So this process will repeat until up to infinity, up to infinity. So this is delta of t or delta t of t. Now, if you multiply this x of t with the delta t of t, why I am always saying that you should multiply means, always please see here, please do remember the basic block diagram we have studied. So in the basic block diagram we are going to apply two input signals to a sampler or to a multiplier. One input is x of t, another input is impulse train. That is a basic block diagram, right? So if you multiply x of t with the delta t of t, now what you will get? Now see here. That means if you clearly observe, the top of the pulses, the top of the pulses. I am talking about the top of the pulses. Okay. Now see it. See in this particular case, the top, how the top of the pulses becomes. It is just looks like the waveform of x of t, x of t. Okay. So you should not have any flat tops here. You should not have any flat. This is a flat top, flat top. So top, flat top. Okay. So if you multiply this x of t with the delta t of t, now see the top of this pulse. Now see the top of the pulse. This is just looks like the input signal, input waveform. You should not have any flat tops here. See why I am saying the flat tops means, next sampling is flat top sampling. Flat top sampling, that is the exactly what we are using for practical applications. We should not use ideal sampler case, we should not use pulse sampling case, and we are only using the flat top approximation. This is a practical sampling process we are using in our laboratories. So that is where I am going to say, or I am going to talking about the flat top approximation, flat top sampling. Okay, now this is pulse sampling. Let me give you the differentiation between the pulse sampling and the flat top sampling. The only thing is if you multiply x of t with the number of impulses defined from minus infinity to plus infinity, plus infinity, you will get the pulses the top of the pulses becomes the original signal x of t. If you just clearly draw the locus of all the impulses, it is just looks like the exactly the given signal, exactly the given signal. Okay, this is not the sampling what we are going to discuss today. We are going to discuss about the flat top sampling. So before going to that, first of all, I have to explain the difference between the flat top sampling and the pulse sampling, right? Now see, already we have discussed about this mathematical expressions, right? This is the flat top sampling, flat top sampling. Now see, flat top sampling. In natural sampling discussed in section means 4.2. Just now we have discussed about the pulse sampling. Pulse sampling, the tops of the pulses follow the waveform of the signals. So just now we have seen that the pulses excess of t is nothing but the sampled signal, sampled signal. So that sampled signal, so top of the pulses follows the sampled signal. See, x of t is the given signal, x of t is the original signal, xs of t is xs of t is the sampled value or the sampled signal obtained from x of t, sampled signal obtained from x of t. This is not the different signal, this is sampled signal obtained from x of t, sampled signal obtained from x of t, right? Now see here, the top of the pulses follows the waveform of the signal. That means in pulse sampling, the top of the pulses will follows the path of x of t, the path of x of t, right? Right? Okay. Now we shall differentiate the flat top sampling when it compared with the natural sampling or pulse sampling. Such type of signals are not frequently employed. So we should not get that type of carrier pulse, or we should not get that type of waveforms, sampled waveforms. Okay, we should not get such type of sampled waveforms. So that is the meaning of the sentence. Such type of signals are not frequently employed. We should not frequently uh, use those type of waveforms. So instead of that, instead of natural sampling or pulse sampling, now we are going to have the flat topped pulses, flat topped pulses. Now I shall explain how the flat topped pulses are going to be. Just wait a moment. Now see how those flat topped pulses are existing. Suppose suppose if I have, again I am considering, so this is x of t, this is x of t. Okay, next one is, see how I am considering the flat topped pulses. Okay, so this is one, this is one, this is one, this is one, and this is one. So now it just looks like this waveform. So which is defined from minus infinity to plus infinity, minus infinity to plus infinity. Now just carefully observe this. If I multiply x of t with this function, what you will get? If I multiply x of t with the impulse function, now see what we will get. Now you see. See, for your understanding, I am going to explain just by drawing the figures. Or simply, I can show you the figure also, but it is not possible to understand. So that is why I am drawing the figures here. Okay. So this is the locus of the original signal x of t. Now, my intention is to obtain the sampled waveform just by multiplying the given function x of t with the impulse trend. Now see here, first I am going to sample. See, now you should get the flat tops that should not follows the path of x of t. That is the difference between the previous sampling and this sampling. This is a flat top sampling. Earlier it is a pulse sampling. So in the case of pulse sampling, if you multiply x of t with impulse train, that will the sampled waveform follows the path of your input waveform. But here, flat tops means so exactly you should get the waveform like this. Later I will explain how this will comes. It does not follows the path of your input waveform. Now you see, now you see, please observe it carefully. See the flat tops. It does not follow the path of x of t. See the flat tops. That means in order to get this type of waveforms, we are using sample and holds device. Sample and holds device. So what it will do, samples SNH device, that is also in short form, sample and hold device is called SNH circuit. So that device is having mainly two switches. Okay. Is it clear? Is it clear? I think it is clear now. Okay, now I'm going to explain how we are getting this type of samplings or this type of output waveforms. Okay, now you see I'm drawing SNH circuit. Okay, so this is another switch. So you will have a capacitor here. So this is S1. Now this has been connected to the input voltage V of t. This is S2 and this is capacitor. So this is the output voltage. output voltage V naught. So here the purpose of capacitor is very very important. So this is the basic sample and holds device which consists of two switches and one capacitor. So whenever the input voltage switch S1 and S2 are switch and S1 and S2 are operated by the pulses, When switch S1 is closed and S2 is in open condition, what happens? The capacitor gets connected to the input voltage. So capacitor starts charging. So it will holds that value. What is that value? The capacitor starts charging towards the input voltage V of t. So this is a sample and hold circuit. This is a very very important concept. SNH device. So when switch S1 is closed and S2 gets open. Okay. Now this path is completely eliminated. You will have only capacitor. So this gets connected to the capacitor. So capacitor starts charging towards V of t. Okay, up to what extent or at what time the capacitor is going to disconnect or capacitor is going to discharge until the next sample is given. So once if we give the sample command to sample and holds device, then switch S1 is closed, yet S2 is open. So at the time of sample point, the capacitor starts charging. That means now see here, if I have given you the sample commands like this. So these are successive samples. If I given a sample command, if I given a sample command at time t is equal to 0 to this, then switch is open. S1 is gets closed. S2 is open. Now this capacitor starts charging. So it will starts charging towards the input voltage Vi. Input voltage Vi. Okay, until the next sample given. So during during this period, it will holds the capacitor will holds the value of input voltage. That means now see here, suppose suppose this is your input signal. Okay, if I have given the sample command at this point. Now this this will this will held constant. This will held constant means the capacitor held that value until the next sample is given. Next sample is given at this one. That means again at this point again the sample command has been given to this. And now see here, it will holds the value for the next sample is again arrives to the sample and holds device. So next sample has been given at this condition. So first sample is this one, second one is this one, third one is this one, fourth one is this one. So if I given the fourth sample command to the SNH device, obviously it will holds the value of like this. Next, so see, so there is no discontinuity. So you should not lost any data. If you add or if you combine all the locus points of these samples, you will get the original data. So this is here x of t is the original data. So at last you should reconstruct that original data from the sampled data. Now see how the samples are there. So this capacitor will hold. Suppose if S1 is open, S2 gets closed means discharging. Capacitor starts discharging. So every time the capacitor, see, most of the times 95% of the cases the name gives you the clear meaning of that concept, sample and hold signal or sample and holds circuit. That means sample command, hold command. There are two commands that has been given to SNH device. Sample command. So whenever you are giving a sample command means obviously your output will measures the magnitude of your input signal. That means at this point, suppose at this time, if if I have given you the sample command, or if I have given the sample command to the SNH device, at this instant, the sample and hold circuit will measures the magnitude of input signal like this. Okay. Now, whenever you are giving a hold command means obviously the capacitor will holds that value, and it will remains as it is until the next sample again arrives to the sample and holds device. Sample and holds device. So that is the meaning of this one, right? Now you see here the sample and holds circuit consists of two switches S1 and S2 as shown in the figure, and a capacitor is placed across switch S1, and a capacitor holds the signal voltage until discharged by the pulse applied to gate gate 2. Now see, now see. I'm sorry, the circuit has not been clearly shown, but whenever we are talking about these switches means obviously now see here, this is switches 1 and this is switches 2. Okay, now this is the gate 1 command and the gate 2 command. This is the sample command, this is the hold command. So whenever G2 has been given, obviously the capacitor S1 or the capacitor is going to be discharged, or it will hold that value. It will hold that value. So already we know that this is XS of T, XPR XS of T is equal to the multiplication of x of k. Now see here, this is already a digital signal and which has been multiplied by a pulse signal which is delayed. So here the k is varying from minus infinity to plus infinity. Already we know that k is equal to minus, which is varying from minus infinity to plus infinity. Now see, so this is the given signal p of t, and this has been multiplied by series of impulses which are defined from minus infinity to plus infinity. Now obviously if you multiply those two functions, you will get p of t minus kt. So already from the given expression you can substitute directly this one, p of t minus kt is equal to this one. Okay. Now see here. So these expressions are already derived in the previous sessions. Okay, there is nothing difficulty. You need not explain much. You just try to write down as simple as possible. As simple as possible. Right? But you should remember the purpose of having sample and holds device. In this particular case of sampling, we are in this sampling process only we are using SNH device. But whereas in the case of remaining two cases, we have not gone to, or we have not seen that type of what do you call, that type of devices are not existing. Okay, not existing. Now you see here, so this is the waveform just now I have drawn here. Just now I have drawn here. Now see the flat tops. So at this particular case, I have given a sample command, and now that the capacitor will hold the value until the next sample arrives. So it will discharge like this. And again the sample command has been given at this point. Now sample command has been given at this point. Sample command is given at this one. Given at this one. See, every time you must remember that. You must remember that. Now this is the case. T minus kt. Now just you vary k is equal to minus infinity to plus infinity. For simplicity, just you substitute k is equal to 0. So what happens if you are getting k is equal to 0? P of t minus capital T. So which is a pulse delayed by tau units or t units. Now this is the case. Okay, so it does not follows the path of your input. See, dashed lines indicates that this is x of t. The original signal you have to reconstruct. The original signal you have to reconstruct. So just by combining the locus points of all these samples, you will get the original data. You will get the original data. What is the original data? So this is the original data. Okay. This is the original data. So you should finally, at last, you should get this function from the sampled value, right? So this is about the flat top sampling. So whatever may be the points we have discussed here, that has been written like this. Okay, you don't worry about this. Next one is signal reconstruction. Signal reconstruction. This is also very very important. Signal reconstruction. So what is the meaning of reconstruction? Have you listened the word reconstruction? A few months back, I think an encounter uh, has been shown in Hyderabad because of some reason. In that particular case, we have listened the word scene reconstruction. Okay, you should reconstruct the original scene as it is. We are not going to present there, but we need to analyze in our mind that so these things are happened in sequence. Okay, so likewise in the signals and systems subject also, the always we should reconstruct the original regenerate the original signal from the sampled data. Okay, where do we use the particular word the reconstruction means? In our subject, we are using digital devices. Most of the times we are talking about the digital equipment. For that digital device, it will accept only the digital input and it will use only digital output. Okay, it won't accept the analog input and it won't give the analog output. But as far as the analysis is concerned, and also the cost point of view, we are always using digital devices over analog devices. So for that purpose only, we have used two type of converters. So first one is A to D converter, and the second one is D to A converter. So you need both the converters for for converting analog to digital and digital to analog. So finally, whatever may be the signal you are using, our intention is again we are going to have the original data. I mean original signal x of t has been given, and you should get x of t only. Okay, so that is the signal reconstruction. So in this case, now see here, this is the block diagram of signal reconstruction. Now, this impulse response h of t, he has mentioned that the low pass filter. He has taken h of t is a low pass filter. Already, when we are dealing with the sampling process, and we have seen so many waveforms. So what is the purpose of having low pass filter? It will eliminate high frequency components from the signal so that you can able to get the original data as it is. So for that purpose, you need to select the proper value of the sampled frequency or the sampling frequency. Okay. So in this case also, that h of t is nothing but the impulse L low pass filter frequency response. Low pass filter frequency response. Now see it. See. So we have discussed the band limited signal x of t can be reconstructed from its samples. If the sampling rate is above the Nyquist, see already we have seen this one also. So what is the frequency rate that we need to choose for getting the original signal from the sampled value? So Fs must be greater than 2 into Fm. So where Fm is the maximum frequency component present in x of t. Now what is the Nyquist rate? So Nyquist rate is this one. This is the Nyquist frequency. Nyquist frequency. Okay. So let the sampled signal is let that means he is going to assume that xs of t is the sampled signal of x of t. Sampled signal, that means already it is sampled. So whenever I use the word sampled means it is a digital signal. Xs of t, even though he has mentioned small t means, but here it is a sampled value. Sampled value. How do you get the sampled value? Sampled value can be obtained from the given continuous time signal only. So that is why we have used xs of t instead of x of n. Sometimes directly we have been given the discrete signals x of n, x1 of n, x2 of n, whatever it may be. But most of the times the available signals are continuous time signals, and you can convert those continuous time signals to digital signals. Okay, so in this case also, let the sampled value of the x of t is xs of t with the sampling period t seconds. T seconds is now we are multiplying the function x of t with an impulse function. So now see here, whenever I use the excess of t, please do remember that you are going to replace small n by, or small t by t is equal to nt. So x of t multiplied by an impulse signal, that means x of t small t is equal to n into capital T. So this is also the sampled value. See, after converting the continuous time domain signals to discrete time domain signals, later we need to represent that signal with x of nt. So now if we apply the Fourier transform on both sides of this expression, on both sides of this expression, what you will get? See, already we have studied about the properties of Fourier transform. So according to the time shifting property or the frequency shifting property, again you are going to get the Fourier transform of the function xs of t. So the Fourier transform of, so this you can also write it as the Fourier transform of capital F of means the Fourier transform. So the Fourier transform of x of xs of t is equal to x of e power j omega. Okay. See, all these expressions already we have seen in the starting of the sampling process. Starting of the sampling process. Don't get confused. Now see here, the frequency spectrum consists of infinite sum of, see, this is a shifted replicas of frequency spectrum of the original signal. So shifted frequencies. Shifted means time shifting, t minus kd. So here, if we vary m is equal to minus infinity to plus infinity, what you will get if just you substitute m is equal to 0 here, omega. So x of j omega, x of j omega. Now substitute m is equal to 1, 2 pi by t, 2, 4 pi by t, 6 pi by t. Likewise, you are getting the replica. Replica is nothing but the mirror image. So whatever may be the response or whatever may be the frequency components you are getting from 0 to infinity, that will be again replica of the signals from minus infinity to 0. Suppose if you are getting one frequency component from 0 to t, again that is a replica of minus t to 0. Okay, so that is the meaning of shifted replicas. Shifted means it is shifting towards plus infinity, and it is shifting from minus infinity. Okay, so to get the original spectrum or original frequency response excess of t is to be passed through the reconstruction filter. So what is the device we are using for having the reconstruction of original signal? Low pass. Indirectly I'm saying that the low pass filter, or you can also consider that as reconstruction, signal reconstruction device. Signal reconstruction device. Simply you can replace the low pass filter to have the original signal. What the function that will be done with the use of low pass filter? It will eliminate the higher frequency components. Okay, already we know about the filter. What is the filter purpose? So we are placing the filters for eliminating the more frequency or higher frequency components, higher frequency. So a lot of noise signals, there should not be any noise signals. Okay, once if you pass higher frequency components through the device means you should get some noise signals, some error signals also. But that is not acceptable. So that is why we are using low pass filters for having the original signal. Okay, so before being processed, first of all the sample value has been passed through this low pass filter, and whose impulse frequency or whose impulse response is h of t, h of t, right? Now see here, this is a very important definition. Now already we know that x of t can be obtained, just wait a minute. Now see here. We already know the convolution property. So convolution, according to that convolution property, the convolution of two time domain signals. So x of t is one our input function convolutes with the h of t. Convolution of two time domain functions. Now here what is y of t, x of t. So at the output of reconstruction device you are getting x of t. So that is why you are getting y of t, or we are equating y of t is equal to x of t. Now what is x of t? This becomes xs of t. So here instead of x of t you will have xs of t, and instead of y of t you will have x of t. Now see here, according to the convolution property of the Fourier transforms, x of t is equal to the convolution of xs of t and h of t. Now already we know that xs of t is equal to this. Just now we have seen this one, this one. Okay, right. Now see here. So just now we have seen excess of t, just we are replacing that excess of t with the sigma n is equal to minus infinity to plus infinity x of nt into delta t of n when it convolutes with the h of t. Now what is the formula? What is the formula? So y of t is equal to integral minus infinity to plus infinity x of tau multiplied by h of t minus tau, x of tau are multiplied by h of t minus tau into d tau, or you will also have one more formula, that is minus infinity to plus infinity h of tau multiplied by x of t minus tau. So this is the convolution direct formula in terms of time domains. See, we have not used Fourier transformations. Just this is the convolution of two time domain signals. You can use any of the two expressions. So in this particular case, I have used the first one, x of tau into h of t minus tau. Now see here, so x sigma n, this you should include the integral which is defined from minus infinity to plus infinity multiplied by sigma n is equal to minus infinity to plus infinity x of nt, x of nt into delta of, here instead of t I have used some other parameter. So in this case also again I'm using the same parameter here, same parameter. I am replacing that small t with the another letter, that is lambda. So this is x of t minus tau, x of t minus tau into sorry, x of tau into h of t minus tau. Okay, t minus tau. So I have taken the tau is equal to lambda here. So here he has defined the basic impulse function definition. So as per the basic impulse function definition, delta of lambda minus n into capital T is equal to 1 for lambda is equal to n into t, and which is equal to 0 not for elsewhere or otherwise. So just you simply substitute, you can take out the summation from the outside of the integration. Why? Because completely that summation. So here the entire integration is in terms of lambdas, lambda. So that's why this is you can take out this constant from outside the integration. So sigma n is equal to minus infinity to plus infinity x of n into t into integral minus infinity to plus infinity. So we should consider the functions as it is. Now on combination of this function, entire function, now you just see here. So delta of lambda minus nt, that is equal to 1. You should see whenever any function is multiplied by impulse function, you should not do integration by considering the limits from minus infinity to plus infinity. Why? Because that impulse function is having value only at a specified or at a particular instant of time. That value or that instant of time here is lambda is equal to n into t. So if I substitute lambda is equal to n into t here, now what you will get? So delta of 0, that is equal to 1 multiplied by h of t minus n into t. Now that is the remaining function. So x of t is equal to sigma n is equal to minus infinity to plus infinity x of n into t into h of t minus nt. So likewise, we are going to get the sampled signal from the, we are going to have the original signal x of t from the sampled signal. So here x of nt is the sampled signal, and which is multiplied by an impulse response, that to the frequency response of the low pass filter, the frequency response of the low pass filter, right? Now see here, the frequency response of low pass filter is expressed as, so frequency response means already we have taken h of t is the impulse response or the frequency response of the low pass filter. Now just he has defined the frequency response of the low pass filter, and later on he has explained the signal reconstruction by considering a simple example. Now if you clearly see, I think it is not clearly seen. Just wait a moment. Okay, now I think it is now visible somewhat better. So like this is a sinc function. This is a sinc function which is defined from minus infinity to plus infinity. This is the what exactly what we need to consider. This is a basic signal. This is a sinc function we need to consider. This is the frequency response. This is the frequency response. Okay, is it not? See the Fourier transform of a rectangular function. See, already we have solved so many problems. We have solved the Fourier transform of a rectangular function, and we have solved the Fourier transform of a triangular function. In both the cases, what is the standard function? So it is in terms of sinc function. Sinc function. If you want, you can please open your notebooks, or please go through the material what I have passed through your WhatsApp group. Okay, already we have solved this problem also. These are basically rectangular function, and the Fourier transform of a rectangular function is a sinc function. Sinc function. Sin x by x form is nothing but a sinc function. So this is the frequency response. That is the original signal, and this is the signal you need to get. So this is the signal you are going to get. You are going to have, and basically we have been sampled this particular signal like this at -2 -1 randomly. I have taken only 5 to 6 samples, and these are the sampled signals. Okay, now shifted replicas means already we have seen the word shifted replicas in the, just now we have gone through this. Okay, so shifted replicas means this same sinc function is replicated from minus infinity to plus infinity. So if I consider, or if I substitute n is equal to 2, now this is 2t. Now if n is equal to -1, this is minus t. So this is 0, and this is t. This is 2t. So likewise the sinc function has been shifted. Likewise the sinc function has been shifted based on the based on the sampled value. So this is -2 and -1, 0, 1, 2, 3. Okay, now see here, 2t minus t, 0, t, and 2t. Okay, if you combine all the locus points, then see how we are going to get the how we are going to get the original signal. Original signal. So this is the sinc function. Now let me explain how we are going to get the original signal x of t. This is the sinc function locus. So which is the maximum value at -2t. Sync function maximum value at this one, and the maximum value at 0, this one, and this one. Okay. Likewise, we are going to have the original data or original signal from the sampled signal. So this is the original signal. So this is the original signal. So this is the original signal you are going to get from the device, right? And this is how we are going to determine the impulse response. Sync, just now we have discussed that the sync function. So how we are getting the sync function? Now see here. So h of j omega. So sine x by x form, sine x by x form. This is what I have explained here just now. Okay, the Fourier transform of a rectangular function is nothing but a sync function. Sync function. So likewise, you are getting the original data, which is to be reconstructed from the sampled waveform, sampled signal. Okay, so that's the end of this particular sampling. Now there are two important problems I need to explain. So if you have any notebook along with you, please note down those problems. Those two are very, very, very important problems. If you are getting a problems from this chapter, those you will get any one of the two problems what we have discussed, what we are going to discuss in this session, right? Now I am sharing my whiteboard here. Right. So determine the Nyquist rate. Determine the Nyquist rate of the following signal. First one is x of t is equal to I shall write it here. First one is x of t is equal to 1 plus cos 200 pi t plus sin 400 pi t. Sin 400 pi into t. So this is the problem what he has given. Determine the Nyquist rate of the following signal. That signal is x of t is equal to 1 plus cos of 200 pi into t plus sine of 400 pi into t. Now for this signal, you have been asked to determine the Nyquist frequency rate. Okay. First of all, before going to proceed that, you should be able to identify the maximum component, maximum frequency component in x of t. Maximum frequency component in x of t. Solution. Now I'm doing the solution here. The highest frequency. So here I am having three components. So x1 of t, and this is x2 of t. Now this is x3 of t. Now what is the highest frequency component of x of t in x1? Highest frequency component 0. Is it not? You should not have any frequency component in x1. So that is why highest frequency component in the first x1 is equal to 0. Now what is the highest frequency component in the second function x2? That is 200 pi cos omega t. Now the highest frequency component in the third one is 400 pi. 400 pi. Now tell me, what is the highest frequency component of x of t? What is the highest frequency component of x of t? So out of these three frequency components, what is the highest? What is the highest frequency component? That is equal to 400 pi, which is equal to omega m. So the first step is you need to determine the highest frequency component in x of t. So here we omega m is equal to 400 pi. Now omega m is equal to 2 pi fm. See, this has been given for 7 marks. Directly you have been asked to determine the Nyquist rate of the following signal. 7 marks. That is the importance of this particular problem. That is why I am taking one more additional class for completing this problem and for completing the chapters. Okay. So first step is you need to consider the original signal as it is, and you need to divide that signal into three parts: x1, x2, x3. And first of all, you should be able to identify the maximum frequency component in these three parts. The first one is 0, and the second signal 200 pi, and the third signal is 400 pi. So again, out of these three components, out of these three frequency components, which one is the highest frequency component? That we are going to equate to omega m. So omega m is equal to 400 pi. Now omega m can be written as 2 pi fm. That should be equal to 400 pi. Is it not? 400 pi. So this pi and this pi gets cancelled. So you will get fm should be equal to 400 by 2 is equal to 4,400. So 400. So 200 Hz. 200. Is it not? Right. Now what is the Nyquist rate? What is the Nyquist rate? So Fn is equal to 2Fm. How do we choose the sampled frequency rate? Okay, sampled frequency rate for signal reconstruction or data reconstruction. That means the sampled frequency or the Nyquist frequency must be greater than or equal to 2 into Fm. Okay, so greater than or equal to 2 into Fm. So likewise, I am considering that Fn is equal to 2 into 200, that is equal to 400 Hz. So what you are asked to determine? What you are asked to determine? Right, only the Nyquist rate, or the Nyquist rate is nothing but the Nyquist frequency. So Nyquist frequency Fn is equal to 400 Hz. So if you select the frequency, sampled frequency is equal to 400 Hz, obviously you should get the original data from the sampled value. Now what is the Nyquist interval? What is the Nyquist interval? So Nyquist interval is equal to T is equal to 1 by Fn. So 1 by 400. 1 by 400. So 1 by 400 means T is equal to, uh, I think 1 by 4.25, 0.25 multiplied by 10 power minus 2 again, seconds. So this is the Nyquist interval. Please carefully see the solution what I did in the whiteboard. Why? Because this is a very important problem in this particular chapter. Most of the times you are getting these type of problems for 7 marks. 7 marks. Okay. Determine the Nyquist rate of the following signal, and the signal has been given as x of t is equal to 1 plus cos of 200 pi into t plus sine of 400 pi into t. The first step is you need to determine the maximum frequency component in the individual signals x1 of t, x2 of t, x3 of t. In x1 of t, you should not have any frequency component. So directly you can substitute fn is equal to there is no maximum frequency component in x1 of t. And the second function, if you consider the cos 200 pi into t, obviously you will have some frequency component, and the maximum frequency component is given by 200 pi. And the third signal, you will have 400 pi. So again, x of t is the combination of x1, x2, x3. So likewise, you have to consider the maximum frequency component in 0, 200 by 400. So directly you can determine that the maximum frequency component is equal to 400 pi. So omega is equal to 400 pi, and omega you have to substitute that omega is equal to 2 pi f. So 2 pi fm is equal to 400 pi, and fm is equal to 200 h. So this is the Nyquist rate that you need to select for getting the signal reconstruction. And if you want to say the Nyquist frequency, that the maximum component, 200 Hz is the maximum component, and the Nyquist frequency rate is equal to 2 into f. So that you will get 400 Hz. Okay, and now later on, if you want to determine the Nyquist time interval, obviously you can treat that as 1 by fn. You will get 0.25 into 10 power minus 2 seconds. So this is about the Nyquist rate and Nyquist time interval. I will give you one more problem as an exercise. You please do this problem at your homes, right? Again, same. Determine the Nyquist rate and Nyquist frequency for the following signal. Now that x of t is equal to x of t is equal to sine 4000 pi t divided by pi t. Solution is exactly similar to that of the previous problem what we did. Okay, so you have been given, but the problem has been changed. Uh, problem has been changed. The way of representation is different. X of t is equal to sine x by xr. So it is a sinc function. Sine 4000 pi into t divided by pi t. Okay. Now this is a problem. You need to focus on this problem to get the answer. So I will write down the answer also. Please note down the answer at some point at somewhere. So Fn is equal to Fn is equal to 4000 Hz, 4000 Hz, and time sample time is equal to 0.25 milliseconds. So this is answer answer for the problem. So with this, we have concluded the third chapter. Third chapter, chapter number 3 has been completed, and from next class onwards, we shall start the new chapter. So I'm leaving the fourth chapter at this moment. First of all, we shall discuss about the Laplace transforms and jet transforms, and after that, we'll definitely have the offline sessions. So whenever offline sessions are there, obviously we shall discuss the fourth chapter in the offline sessions. Or otherwise, just we will follow the same online teaching for the fourth chapter also. But why I'm skipping that fourth chapter means that that is somewhat difficult to understand also for you people. So Laplace transforms, jet transforms, already you have seen these two types of transformations in your mathematics, and similarly in the case of network theory, obviously those two topics are also very easy to remember, and very easy to get the concepts. So that is why I'm going to cover those two chapters first, and the latter we have to see the fourth chapter at the last, right? So in the next class we shall start the Laplace transformations. So that's the end of section. If you are having any doubts, you please raise your doubts. Students, do you have any doubts regarding the today's session? If you do not have any doubts, I shall leave or I shall end the session now. Okay, thank you very much. In the next class, we shall start a new chapter that is Laplace transforms. Okay, I think a timetable has been changed. Please go through the timetable and attend the classes properly. And one thing is very very important. See, for RES class, every time the link has been shared in the group itself, please join the group by clicking on that group link is different and our link is different. Okay, for section A, the remaining four subjects link is common, and the fifth subject RES link is different. That is common for the group 1 and group 2. Okay, Sir will share the link also for every time. Please go through the modified timetable. Thank you.